Hello, welcome back to PhysioDesigner tutorial series. So far in this series, we investigated several control strategies of the inverted pendulum using simulations. In the process, we observed graphs of simulation results. In this time, a way to visualize the simulation results using morphological object is demonstrated, which can give more intuitive understanding. The goal is to visualize the swaying of the inverted pendulum as like shown here. This can be achieved quite easily with PhysioDesigner. Load the Model 3 which we created in the previous tutorial. In the Model 3, we set noise equals 0, but now let's add noise at first, and run a simulation with Flint. Length is 300, and output simulation data 1 point per every 10 points. Data shows this kind of dynamics, and save the data into a file with ISD format. We will show this data with animation. Firstly, we need to define a morphological data of the inverted pendulum. Right-click on the module, and select Morphology, and edit Morphology. In a dialog, we will define geometries. One module can integrate one morphological data, which is composed of multiple geometries. Hence, here we define a geometry, set name of the geometry, and set the dimension. Here it is 3. It is possible to define a geometry in two ways. One is to select one shape from simple primitive shapes, in other words, predefined shapes. The other way is to use an external file defining a morphological information. Now we use a primitive shape. To create the bar shown in the beginning of this tutorial, select cuboid in the combo box. To define one cuboid, we need to set 3 parameters, that is lengths of x side, y side, and height. Now, set 1, 1, and 20, respectively. Then click Add button, and Apply button. Clicking a View button, you can check the shape of the cuboid, then close the dialog. Next, we will define the angle of the inverted pendulum using the physical quantity theta. Right-click on the module, and select Edit Frame Coordinate. The frame coordinate is a coordinate sticked on the module. All geometries are defined in this coordinate. Hence, if we rotate the coordinate, geometries defined in the coordinate are also rotated accordingly. If this module has a child module, the frame coordinate of the child module is defined as a relative coordinate with respect to this module's coordinate. There are 3 ways to define the rotation of the coordinate, that is, matrix, Euler angle, and quaternion. Here let's use Euler angle, and put theta for the first rotation around x-axis. The rest of rotation angles are 0. Then go to the Morphology in the context menu, and this time, select Morphospace. You see the long bar. Because the shape is too simple, the meaning of 4 panels are not clear, but actually, right bottom panel shows the object in 3-dimensional space, and the other 3 panels shows projection views on the ZY, ZX and YX planes, respectively. Go to View menu, and select Show Morphodynamics. It asks you to select a simulation result. By giving the simulation result file, the theta which is used to define the rotation of the coordinate can refer the values in the data file, and be used to create animation. A small dialog with time slider, and play, back and forward buttons appears. By clicking a play button, animation starts. You can directly control the time slider as well. The bar fluctuates according to the simulation data, but we need to modify. Did you notice that the center of the bar is the center of the rotation, which is not good for this case, because we want the bar rotate at the position of the ankle, which is bottom of the bar. Besides, the fluctuation is too small to see. For the visualization, we want to exaggerate the amplitude of the sway. Let's modify these 2 points. Firstly, create a new physical quantity of variable parameter type to define the 10 times exaggerated rotation motion. In the physical quantity dialog, create a physical quantity named angle, and in the implementation, define it as 10 times theta. And then, in the frame coordinate definition, use angle instead of theta. Okay, next, move the bar a little bit upper side, along z-axis. Now the center of the bar is at the origin of the coordinate. By shifting it upper side by 10 units, the bottom of the bar comes at the origin of the coordinate. Okay, close the dialog, and save the model. And run a simulation to get the simulation data for the physical quantity angle. We can confirm that angle is 10 times larger than theta in the amplitude. Save the simulation data in ISD format. Then go to the Morphospace again and call Morphodynamics. Select the new simulation data and move the time slider. You see, now the vertical bar is fluctuating with visible amplitude. It is also possible to export a movie. If we define the morphology using external files instead of a simple primitive shape, the simulation data of the inverted pendulum can be visualized, for example, with the whole body skeletal system like shown here. That's all for this tutorial. Thank you for watching until the end. See you until next time. Goodbye.